There is a question that physics cannot answer. Not because we lack data, not because we lack intelligence, but because the question itself may not make sense. What came before the Big Bang? It feels like the most natural question imaginable. Everything in your experience has a before. Before you woke up this morning, you were asleep. Before this building existed, there was empty land. Before the Earth formed, there was a cloud of dust and gas orbiting a young star. The chain of befores stretches backward through memory, history, and geological time without resistance, until it reaches the beginning of the universe. According to our best measurements, the universe began 13.8 billion years ago. Not just the matter inside it, not just stars and galaxies and planets. Space itself began. Time itself began. The very framework that allows events to occur came into existence in that moment. And that is where the problem begins. Because if time itself began with the Big Bang, then the word before loses its meaning. Before is a temporal concept. It requires time to exist. Asking what came before the Big Bang may be like asking what lies north of the North Pole. The question contains an assumption that breaks down when examined closely. And yet, the question refuses to disappear. Our minds resist the idea of an absolute beginning. We are creatures shaped by cause and effect. Every event we know has a cause. Every beginning has something that triggered it. The universe began, so something must have caused it to begin. The logic feels unavoidable. Physics, however, is under no obligation to satisfy intuition. If we rewind the universe using the equations we trust most, a strange picture emerges. Galaxies rush toward each other. Space grows hotter and denser. Stars unfuse, dissolving into primordial hydrogen and helium. Atoms break apart. Electrons are stripped from nuclei. Matter dissolves into a seething plasma. Rewind further, and even atomic nuclei disintegrate. Protons and neutrons separate. The universe becomes a dense soup of fundamental particles, then a sea of pure energy compressed into a space smaller than a single atom. Smaller still. Temperature and density climb without limit. And then, at 13.8 billion years ago, our equations stop working. They do not give us answers. They give us infinities. They give us contradictions. They give us nonsense. This boundary is called a singularity. It is not a place we can describe. It is a signal that our understanding has failed. Einstein's theory of general relativity predicts that compress enough mass into a small enough space, and space-time itself becomes infinitely curved. The mathematics can describe the approach to this state, but not the state itself. Quantum mechanics does not rescue us. It excels at describing the smallest scales of reality, but it does not cooperate with gravity. When we attempt to apply both theories to the conditions of the early universe, they conflict. Smooth space-time clashes with quantum uncertainty. Probability collides with curvature. We do not have a working theory of quantum gravity, and without it, we cannot describe the beginning. This leaves us in an unusual position. The Big Bang is not just a beginning in time, it is a boundary of explanation. Beyond it, our most successful theories refuse to speak. So what does that mean for the question of before? Some physicists argue that the question is meaningless. If time began with the Big Bang, then there is no earlier moment to reference, no prior state, no hidden chapter waiting to be uncovered. The universe simply began. Others are not satisfied with that answer. They suggest that the Big Bang was not the beginning, but a transition, a phase change in something deeper. Perhaps the universe existed in a different form before expanding violently into the space-time we inhabit. Perhaps time itself behaves differently at fundamental scales, losing the simple directionality we experience. Some theories propose bouncing universes where contraction precedes expansion. Others imagine eternal inflation, where our universe is one bubble among countless others forming in a larger cosmic process. Still others suggest that time may be emergent, a byproduct of deeper relationships rather than a fundamental feature of reality. Each idea attempts to restore the word before without breaking physics. None have been confirmed. What is remarkable is how far we can see. We can describe the universe with precision fractions of a second after the Big Bang. We can model conditions 1/trillionth of a second into cosmic history. We can measure the afterglow of the universe's earliest light with extraordinary accuracy. But that final boundary remains. The moment where time itself begins. The point where causation loses meaning. The instant beyond which language fails. This is not a failure of curiosity, it is a collision between human intuition and the structure of reality itself. We are asking a question shaped by everyday experience in a universe that does not behave in everyday ways. To understand whether before the Big Bang is a real question or a conceptual trap, we must first understand what the Big Bang actually was, and what it was not. Only then can we see whether there was ever anything for before to refer to at all. The Big Bang is not what most people imagine when they first hear the term. It wasn't an explosion, not in any conventional sense. When you picture an explosion, you probably see something expanding outward into empty space. A bomb detonates and debris flies outward from a central point into the surrounding air. A star goes supernova, hurling its outer layers into the darkness between stars. There's always a place where the explosion happens, and a larger space into which the explosion expands. The Big Bang was nothing like this. It wasn't an explosion in space, it was an expansion of space itself. This distinction matters more than it might seem at first. Every point in the universe was present at the Big Bang. The space you're occupying right now, the space between stars in distant galaxies, the space in the farthest reaches of the observable universe. All of it emerged from that initial state. There was no edge. There was no center. There was no external void into which the universe expanded. If you could have been present in those first moments looking around, you wouldn't have seen a bright point of light in one direction, with darkness in the other directions. You would have seen intense light and energy in every direction, uniformly. Every location was the center. Every point was experiencing the same expansion. This is difficult to visualize because it contradicts our everyday experience. But the evidence for this view is remarkably strong. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us. More surprisingly, he found that the farther away a galaxy is, the faster it's receding. This wasn't because something pushed those galaxies outward through space. It's because the space between us and those galaxies is expanding, carrying them along with it. Imagine dots on the surface of a balloon as it inflates. Each dot moves away from every other dot, not because the dots are moving across the balloon's surface, but because the surface itself is stretching. Run this expansion backward in time, and you find that the universe was once much smaller, much denser, and much hotter. All the matter and energy that now fills billions of light-years of space was compressed into a region far smaller than a single atom. Then there's the cosmic microwave background radiation. In 1964, two scientists detected a faint radio signal coming from every direction in space. This wasn't noise in their equipment. It was the afterglow of the Big Bang itself, cooled by expansion over billions of years. When the universe was about 380,000 years old, It had cooled enough for electrons and protons to combine into neutral hydrogen atoms. At that moment, photons that had been constantly scattering off free electrons could finally travel freely through space. Those photons are still traveling. They've been stretched by cosmic expansion from visible light into microwaves, but they're still here, a direct echo from the early universe. The pattern of tiny temperature variations in this cosmic background radiation matches predictions with extraordinary precision. It shows us ripples in the density of the early universe, seeds that would eventually grow into galaxies and clusters of galaxies. It provides a baby picture of the cosmos, taken when the universe was less than 1% of its current age. We can trace cosmic history back remarkably far with confidence. 1 second after the Big Bang, the universe was hot enough that nuclear fusion was occurring everywhere at once, forging the first atomic nuclei. Before that, in the first second, quarks and gluons combined to form protons and neutrons. Earlier still, in the first microsecond, the universe was too hot for composite particles to exist at all. But there's a limit to how far back we can confidently project our understanding. At approximately 10 to the negative 43 seconds after the Big Bang, we encounter what's called the Planck time. This is the boundary where quantum effects of gravity become important, where the smooth space-time of general relativity breaks down into something unknown, possibly a foam of quantum fluctuations at scales far too small to observe directly. Before the Planck time, we have theories but no certain knowledge. Our equations produce infinities and paradoxes. We're extrapolating beyond the domain where our physics has been tested. It's like trying to use a map of your city to navigate a different planet. The map might be accurate for where it was designed, but it won't help you somewhere completely different. This is the Planck wall, and it represents the current limit of empirical cosmology. Beyond it lies the realm of theoretical speculation, of ideas that are mathematically elegant and internally consistent but not yet testable by observation. What many cosmologists emphasize is that the Big Bang theory describes the evolution of the universe from an early, hot, dense state. It describes expansion, cooling, the formation of structure. It's been extraordinarily successful at explaining observations, but it doesn't necessarily describe the absolute beginning of existence. It doesn't tell us whether there was something before that hot, dense state, or whether the very concept of before applies. The singularity at the beginning, where density and temperature become infinite, might be a real feature of nature, or it might be an artifact of applying general relativity beyond its valid range. Just as Newtonian physics breaks down at very high speeds, requiring relativity to take over, general relativity might break down at very small scales, requiring a theory of quantum gravity that we don't yet possess. The universe at the Planck time was unimaginably different from anything we can observe today. It was hotter than the core of any star. It was denser than a neutron star. Space and time themselves were intertwined in ways that challenge our understanding. The moment our equations break down, that infinitesimal fraction of a second is where the real mystery begins, and where several remarkable theories attempt to peer beyond. One of the most successful ideas in modern cosmology emerged from a puzzle about the universe's structure. The puzzle was this: why does the universe look essentially the same in every direction we observe? The cosmic microwave background radiation, that afterglow from the early universe, has almost exactly the same temperature, no matter where we point our telescopes. The difference between the warmest and coldest spots is less than 1 part in 100,000. This uniformity seems unremarkable until you realize that regions of space on opposite sides of the observable universe have never been in contact with each other. They've never had time to exchange light or information, and yet they have the same temperature, the same density, the same properties. How did they know to match? How did distant, disconnected regions of space coordinate to have identical conditions? The answer, proposed by physicist Alan Guth in the early 1980s, is cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. Space didn't just grow, it doubled in size, then doubled again, then again, over and over in an almost incomprehensibly short time. A region smaller than an atom inflated to the size of a grapefruit, then to astronomical scales, all in less time than it takes light to cross the width of a proton. This violent expansion would have stretched a small, uniform patch of space into a region large enough to encompass everything we can now observe. The uniformity we see isn't because distant regions communicated. It's because they all came from the same tiny patch before inflation flung them apart. Inflation solves other puzzles too. It explains why space appears flat rather than curved. It explains why we don't see magnetic monopoles or other exotic relics that early universe theories predict should exist. The mathematics works beautifully. The predictions match observations. Inflation has become a cornerstone of the standard cosmological model. But inflation has an unexpected implication, one that extends far beyond explaining our universe's structure. The mechanism that drove inflation was likely a quantum field, something permeating all of space, stuck in a high-energy state. As this field rolled down to a lower energy state, it released energy that drove the exponential expansion. Eventually, in our region of space, the field reached its lowest energy state. Inflation ended. The energy was converted into matter and radiation, creating the hot, dense conditions we call the Big Bang. But here's the crucial insight. Quantum fields are subject to quantum fluctuations. They don't behave uniformly everywhere at once. In some regions, the field might roll down to its low energy state quickly. In other regions, quantum fluctuations might push it back up, keeping inflation going. Once inflation starts, it becomes very difficult to stop completely. Regions where inflation ends become bubbles of normal space, expanding at ordinary rates, filled with matter and energy. But the space between these bubbles continues to inflate, and that inflating space creates more space, which itself continues to inflate. The process feeds on itself, creating more and more volume in which new bubbles can form. This is eternal inflation. Once it begins, it never truly ends. It produces an infinite number of bubble universes, each undergoing its own Big Bang, each potentially with different physical properties. Our universe would be just one bubble in this vast, eternally inflating expanse. What we call the Big Bang would be the moment when inflation ended in our particular bubble, when the energy of the inflaton field converted into the particles and radiation that fill our cosmos. But beyond our bubble's edge, inflation continues. Other bubbles form, each one home to its own universe with its own history. The bubbles don't collide often because the space between them is expanding so rapidly that they're pushed apart faster than they can grow. Each bubble is like an island universe, causally disconnected from the others. Light from another bubble could never reach us, no matter how long we wait. They exist beyond our cosmic horizon, permanently inaccessible. In this picture, asking what came before our Big Bang becomes a different kind of question. Our Big Bang was a local event, the birth of our particular bubble. But the larger process of eternal inflation extends backward in time without limit. There's no first moment when inflation began. It's been happening forever, producing bubble universes continuously. Each bubble might have different physical constants. The strength of gravity could vary. The mass of electrons could be different. The number of spatial dimensions might not be 3. This depends on how the inflaton field behaves as it settles into different configurations in different bubbles. Most of these universes would be sterile, inhospitable to any form of complexity. But in an infinite multiverse, every possibility that can occur will occur, including universes like ours where the constants happen to allow for stars, planets, and life. The philosophical implications are profound. If eternal inflation is correct, there's no need for a beginning, no moment of creation requiring explanation. The multiverse simply exists, generating bubble universes endlessly. Cause and effect become local properties of individual bubbles, not features of reality as a whole. Of course, this comes at a cost. We can never observe these other universes. The theory makes predictions about our own universe that we can test, but the multiverse itself lies beyond empirical verification. Some physicists find this troubling, arguing that science should restrict itself to testable claims. Others counter that if inflation is real and if the mathematics inevitably leads to eternal inflation, then we must accept the implications, even if they're impossible to observe directly. The theory also doesn't truly eliminate the mystery of origin. It replaces the question of what came before our Big Bang with a deeper question. Why does inflation happen at all? Why do quantum fields exist? Why do they have the properties that lead to eternal inflation? We've pushed the mystery back, but we haven't made it disappear. But inflation, for all its explanatory power, still requires something to inflate. Another framework suggests the universe may cycle through phases, with our Big Bang merely one turn in an eternal cosmic wheel. There's something aesthetically appealing about the idea of cycles. Day follows night follows day. Seasons rotate through spring, summer, autumn, winter, and back to spring again. Breathing in, breathing out. Birth and death and rebirth. Perhaps the universe itself follows a similar pattern. The idea of a cyclic universe is ancient, appearing in various forms across different cultures and philosophies. But in modern physics, it takes on a more precise form, grounded in mathematics and observational constraints. The classic version imagines the universe expanding from a Big Bang just as we observe. Galaxies rush apart, space grows larger and cooler, but gravity eventually wins. The expansion slows, stops, and reverses. The universe begins to contract. Galaxies fall back toward each other. Space shrinks, temperature rises. Eventually, everything collapses back into an incredibly hot, dense state, a big crunch that mirrors the Big Bang. But then, instead of ending, the universe bounces. The contraction reverses into a new expansion. A new Big Bang emerges from the ashes of the old universe. The cycle begins again, repeating endlessly into both the past and future. In this picture, our Big Bang wasn't the beginning of everything. It was just the latest in an infinite series of cosmic rebirths. What came before? Another universe, similar to ours or perhaps very different, running through its own cycle of expansion and contraction. The appeal is obvious. There's no need to explain an absolute beginning, no requirement for something to arise from nothing. The universe has simply always existed, transforming through cycles, but never truly beginning or ending. But there's a serious problem with this simple cyclic model. It's called entropy. Entropy is a measure of disorder, of the number of ways a system can be arranged. The second law of thermodynamics states that entropy always increases in a closed system. Things become more disordered over time. A cup of hot coffee cools to room temperature. A star burns through its fuel and disperses its energy into space. Entropy rises inexorably. If the universe contracts and bounces, that entropy doesn't disappear. It carries over into the next cycle. Each new cycle would inherit the entropy of all previous cycles. Over infinite cycles extending into the past, entropy should have already reached its maximum value. The universe should be in a state of maximum disorder, with no usable energy remaining, no structure, no stars, no galaxies. The fact that we observe a relatively ordered universe with low entropy suggests that either the cycles haven't been going on forever, or something is wrong with the simple cyclic model. Modern cyclic theories attempt to address this problem in various ways. One approach, called the ekpyrotic model, involves extra dimensions of space beyond the familiar three. In this picture, our universe is a three-dimensional membrane, or brain, floating in a higher dimensional space. There's another brain nearby, separated from ours by a tiny gap in the extra dimension. Periodically, these two brains collide. The collision releases enormous energy, creating the hot, dense conditions we associate with the Big Bang. The brains then bounce apart, spending trillions of years in a slow approach before colliding again. Each collision is a Big Bang. Each period between collisions is a cycle. The genius of this model is that it avoids the singularity entirely. There's no moment when density and temperature become infinite. The brains never quite touch at a single point. Instead, they collide across their entire surface, producing a gentler, more controlled transformation from contraction to expansion. Another approach comes from loop quantum gravity, a theory that attempts to merge quantum mechanics with general relativity. In this framework, space itself is not infinitely divisible. At the smallest scales, it has a discrete structure like pixels on a screen. When you try to compress matter and energy into smaller and smaller volumes, quantum effects become important. Loop quantum gravity suggests that as the universe contracts toward what classical physics would call a singularity, quantum effects create a repulsive force. This quantum repulsion prevents the universe from collapsing to a point. Instead, the contraction smoothly transitions into expansion. The universe bounces. Computer simulations of loop quantum cosmology show that information can pass through the bounce. The universe on the other side of the bounce inherits properties from the previous cycle. It's not a complete reset. Some structure, some memory of what came before, persists. These models raise intriguing questions about what carries through from one cycle to the next. Could the fundamental constants of physics change? Could the dimensionality of space be different in each cycle? Or are some properties necessarily conserved, creating a kind of cosmic inheritance? There's also the question of whether infinite cycles into the past constitute a true beginning or not. Mathematically, an infinite series can extend backward without end. But philosophically, some argue that infinite past events lead to paradoxes. If the universe has been cycling forever, how did we reach this particular cycle? Why isn't the count of previous cycles itself infinite? These cyclic models are harder to test than you might expect. The bounce occurs under conditions so extreme that any information about the previous cycle is largely erased. The cosmic microwave background might contain subtle signatures of what happened before, but extracting those signatures from noise is extraordinarily difficult. What the cyclic models offer is an alternative to the notion of an absolute beginning. They suggest that time extends infinitely in both directions, that our Big Bang was a transition rather than a creation. The universe didn't begin. It simply changed. But they also shift the mystery rather than solving it completely. Instead of asking what caused the Big Bang, we now ask, what maintains the cycle? What ensures that each bounce leads to another expansion? Why do the physics work this way rather than some other way? These cyclic visions imagine time extending infinitely backward, but another perspective suggests that time itself may not be what we think it is, that it might emerge from something more fundamental. Time feels fundamental to existence. You experience it flowing steadily forward, carrying you from past through present into future. Your memories lie behind you. Your plans stretch ahead. The sensation of time's passage seems as basic and irreducible as anything in your experience. But physics suggests something stranger might be true. In quantum mechanics, time plays a unique role. It's the parameter by which everything else changes. Position, momentum, energy all evolve according to equations that contain time as an independent variable. Time ticks forward, and the quantum state changes in response. But in general relativity, Einstein's theory of gravity, time is part of space-time, woven together with the three dimensions of space into a single four-dimensional fabric. Time is relative. It flows at different rates depending on how fast you're moving and how deep you are in a gravitational field. There's no universal now, no cosmic clock ticking the same for everyone. These two descriptions of time don't match. And when you try to create a theory of quantum gravity, combining quantum mechanics with general relativity, the tension becomes acute. One of the central equations of quantum cosmology is called the Wheeler-DeWitt equation, named after the physicists who formulated it. This equation describes the quantum state of the entire universe. But something remarkable happens in this equation. Time disappears. The Wheeler-DeWitt equation contains no time variable. It describes a static, unchanging quantum state. Nothing evolves, nothing becomes. The universe simply is, frozen in a timeless mathematical structure. This seems to contradict everything we observe. We experience time flowing. We see change happening. Clocks tick, stars evolve, galaxies move. How can the fundamental equation describing reality contain no time? The resolution, some physicists suggest, is that time is emergent. It's not a fundamental feature of reality, but something that arises from deeper, timeless physics. Just as temperature emerges from the average motion of molecules, even though individual molecules don't have temperature, time might emerge from quantum correlations between different parts of the universe. Imagine a clock and a system being observed. The quantum state describes both together in a timeless way. But within that timeless description, there's a correlation. When the clock reads one configuration, the system is in one state. When the clock reads a different configuration, the system is in a different state. An observer using the clock would perceive time flowing and the system evolving. But from outside, from the perspective of the Wheeler-DeWitt equation, there's no time, only correlations between subsystems. This perspective transforms the question of what came before the Big Bang. If time emerges from the quantum state of the universe, then the Big Bang isn't the first moment of time. It's a configuration, a particular correlation pattern within the timeless quantum state. Asking what came before assumes that time is fundamental, when it might not be. Stephen Hawking and James Hartle proposed what they called the no-boundary proposal, another approach to quantum cosmology. Their idea begins with a mathematical trick used in quantum mechanics called imaginary time. In ordinary mathematics, numbers can be real or imaginary. Real numbers lie on a line. Imaginary numbers involve the square root of -1, extending into a perpendicular dimension. In quantum field theory, sometimes calculations are easier if you replace real time with imaginary time, do the calculation, then convert back to real time at the end. It's a computational tool, not usually thought of as physically meaningful. But Hawking and Hartley suggested taking imaginary time seriously in the context of the early universe. As you approach the Big Bang using imaginary time instead of real time, something interesting happens. The singularity, that point of infinite density and temperature, smooths out. Imagine the surface of the Earth. If you ask what's north of the North Pole, the question doesn't make sense. The North Pole is the northernmost point. You can't go further north. But this doesn't require a boundary or an edge. The surface just curves in a way that makes north of the North Pole undefined. Similarly, in imaginary time, space-time becomes smooth and finite near the Big Bang. There's no singularity, no edge, no boundary. The universe is finite in imaginary time but has no beginning, just as the Earth's surface is finite but has no edge. When you convert back from imaginary time to real time, you get a universe that appears to have a beginning, but that beginning emerges from a smooth, timeless quantum state. The no-boundary proposal suggests that the universe's quantum state has no initial conditions imposed externally. It's completely self-contained. The laws of physics determine the state uniquely. There's no need for something before to set the initial conditions, because there is no initial moment in the fundamental description. This is deeply strange. It means that time, which feels so immediate and real to you, might be an approximation, a useful way of describing reality that works in our everyday experience but breaks down in extreme conditions. It also means that our intuitive notion of causality might be limited. We think of causes preceding effects in time. Event A happens, then event B happens as a result. But if time is emergent, this temporal ordering might be a feature of our perspective rather than something fundamental. The quantum state of the universe wouldn't exist in time. It wouldn't evolve or change. It would simply be, containing within its mathematical structure all correlations between different configurations, including those we interpret as temporal sequences. Critics of these ideas point out that they're highly speculative. We have no direct evidence that time is emergent. We can't test the Wheeler-DeWitt equation or the no-boundary proposal observationally. These are mathematical frameworks that might describe reality, but they could also be elaborate constructions that miss something essential about how the universe actually works. Yet they offer a genuinely different answer to the question of what came before. Not another universe, not an eternal cycle, not an inflating multiverse, but a timeless quantum reality from which time itself emerges, making the question of before meaningless at the deepest level. If time itself is an emergent property of our universe, then the very fabric of reality might arise from something even stranger, a quantum foam of possibilities where existence and non-existence blur together. In quantum mechanics, empty space is never truly empty. Even in a perfect vacuum with no particles present, the quantum field itself fluctuates. Virtual particles pop into existence in pairs, a particle and its antiparticle, live briefly, then annihilate each other and disappear. This happens constantly, everywhere, at scales too small and timescales too brief to observe directly. These quantum fluctuations aren't just theoretical, they produce measurable effects. The Casimir effect, for instance, shows that two metal plates placed very close together in a vacuum experience a force pushing them together. This happens because the quantum fluctuations between the plates are restricted by the narrow gap, while fluctuations outside the plates occur freely. The imbalance creates pressure. It's a tiny effect, but it's real and measurable. So empty space, what physicists call the quantum vacuum, seethes with activity. Particles borrow energy from nothing, exist briefly, then pay the energy back when they annihilate. This borrowing is allowed by Heisenberg's uncertainty principle, which states that you can't simultaneously know both the energy of a system and the time interval you're measuring it. For very short times, energy conservation can be violated temporarily. The shorter the time interval, the larger the energy fluctuation that's permitted. At the Planck time, that incredibly brief moment we encountered earlier, the energy fluctuations can be enormous. In principle, an entire universe's worth of energy could fluctuate into existence, provided it happens quickly enough. This leads to a remarkable idea. Perhaps the entire universe is a quantum fluctuation. Perhaps our cosmos, with all its matter and energy, its galaxies and stars and planets, emerged spontaneously from the quantum vacuum through a process fundamentally similar to those particle-antiparticle pairs that pop in and out of existence. At first, this seems to violate energy conservation on a cosmic scale. Creating a universe requires an enormous amount of energy. Where does it come from? The answer lies in gravity. Gravity is attractive, binding things together. In physics, this binding is described as negative potential energy. When you lift a ball against Earth's gravity, you add energy to it. When the ball falls, that energy is released. The ball's position in the gravitational field represents stored negative energy. On a cosmic scale, the gravitational binding energy of all the matter in the universe is negative and enormous. If you calculate the total positive energy from all matter, radiation, and the kinetic energy of expansion and add to it the negative gravitational potential energy, the sum appears to be very close to zero. The universe's total energy might be exactly zero. If the total energy is zero, then the universe doesn't violate energy conservation by existing. It's the ultimate free lunch. The positive energy of matter and motion is precisely balanced by the negative energy of gravitational attraction. Create both simultaneously and you've created something from nothing without breaking any conservation laws. This raises a profound question. If the universe's total energy is zero, and if quantum mechanics allows fluctuations that briefly violate energy conservation, then why shouldn't a universe fluctuate into existence? The process would work something like this. In the quantum vacuum, a tiny region of space undergoes a massive fluctuation. Space itself expands rapidly, creating a bubble of inflating space-time. The energy of the inflaton field becomes matter and radiation. Gravity creates negative potential energy to balance it. The bubble is our universe, now large and classical, and no longer quantum in nature, but it started as a random quantum event. This isn't science fiction. It's a serious proposal by physicists like Alexander Vilenkin and others, grounded in quantum field theory and general relativity. The mathematics works. The physics is consistent with what we know. But there's a philosophical problem that can't be ignored. What exactly does nothing mean in this context? When physicists talk about the quantum vacuum, they're describing a state with no particles, but they're not describing absolute nothingness. The quantum vacuum exists within space-time. It's governed by quantum field theory. It has properties, structure, laws. It's a very specific kind of nothing, far from the philosophical concept of absolute non-existence. The quantum fields themselves exist. The mathematical framework of quantum mechanics exists. The laws that allow fluctuations exist. Some would argue that these are all something, not nothing. You haven't explained where the universe came from if you've simply pushed the question back to asking where quantum fields and their laws came from. Physicists sometimes respond that these laws are simply the way reality is, requiring no further explanation. The laws of physics aren't caused by anything. They're brute facts about existence. Asking why they exist is like asking why mathematical truths are true. 2 + 2 = 4, not because something caused it to be so, but because it's necessarily true within the logical structure of mathematics. Yet the question persists. Even if quantum fluctuations can create universes, Why does the quantum vacuum exist? Why do fields have the properties they have? Why is there something rather than absolute nothing? There's another aspect to consider. In quantum mechanics, if something can happen, it will eventually happen given enough time or opportunities. The probability might be extremely low, but in an infinite quantum vacuum existing for infinite time, even improbable events become certainties. If a universe can quantum tunnel into existence, then universes will appear. Not just one universe, but many, perhaps infinitely many. Each one a bubble nucleating in the quantum foam, each one potentially with different properties depending on how the quantum fields settle into their configuration. This version of universe creation doesn't require a cause in the traditional sense. It's probabilistic. The universe exists because it's possible for it to exist. And what's possible in quantum mechanics eventually becomes actual. The picture this paints is strange and somewhat unsettling. There's no intention behind creation, no purpose, no design. The universe appears spontaneously, like a radioactive atom decaying at a random moment. It's a fundamentally quantum event, governed by probability rather than deterministic causation. Critics point out that this explanation, like eternal inflation or timeless quantum cosmology, can't fully answer the deepest question. You've explained how universes might emerge from the quantum vacuum, but you haven't explained why there's a quantum vacuum with these particular properties in the first place. The mystery has been reduced, perhaps, but not eliminated. Yet even quantum fluctuations occur within the framework of quantum laws themselves. This leads us to perhaps the most profound question. Why do these laws exist at all? And could our universe be just one possibility in an infinite mathematical landscape? Mathematics has a peculiar quality that philosophers have puzzled over for centuries. Mathematical truths seem to exist independently of physical reality. The Pythagorean theorem was true before humans discovered it. It would remain true even if the universe disappeared tomorrow. Mathematical structures appear to have a kind of eternal existence outside of space and time. This has led some physicists to wonder whether mathematics isn't just a tool for describing reality, but is reality itself. The physicist Max Tegmark has proposed what he calls the mathematical universe hypothesis. The core idea is that the physical universe isn't just described by mathematics. It is mathematics. Our universe is a mathematical structure, and it's one among many such structures that exist in a kind of Platonic realm. In this view, asking why the universe obeys mathematical laws is like asking why circles are round. The universe obeys mathematical laws because it is a mathematical structure. The laws of physics aren't imposed on reality from outside. They're intrinsic properties of the mathematical object that is our cosmos. This perspective treats existence as a property of mathematical structures themselves. A mathematical structure doesn't need to be instantiated in physical matter to exist. It exists by virtue of being logically consistent and well-defined. Our universe exists in the same way that the Mandelbrot set exists, as a coherent mathematical object with internal relationships and structure. If this is true, then every possible mathematical structure exists in this abstract sense. There's no selection process determining which structures are real and which aren't. They're all equally real, existing as mathematical objects. Our universe is simply the particular mathematical structure that we inhabit, the one that includes conscious observers like us. This leads to a vast landscape of possible universes, each one corresponding to a different mathematical structure. Some would have 3 dimensions of space. Others might have 4, or 7, or 10. Some would have quantum mechanics. Others might have entirely different physical laws. Some would have time flowing forward. Others might have more complex temporal structures. Most of these mathematical structures would be sterile, incapable of supporting any form of complexity, let alone life and consciousness. The laws might be too simple, allowing only static configurations, or too chaotic, preventing stable structures from forming. Only a small subset of possible mathematical structures would have the delicate balance of complexity and stability needed for observers to exist. This brings us to the anthropic principle, an idea that's as controversial as it is powerful. The anthropic principle observes that our existence as conscious observers places constraints on what we can observe about the universe. We cannot observe a universe that's incompatible with the existence of observers. This sounds trivial, almost tautological, but it has deep implications. Consider the fundamental constants of nature: the strength of gravity, the mass of the electron, the charge of the proton, the strength of the nuclear forces. These values appear to be finely tuned for life. If gravity were slightly stronger, stars would burn out too quickly for planets to form and life to evolve. If it were slightly weaker, stars might never ignite fusion. If the strong nuclear force were a bit different, atomic nuclei couldn't form. If the electromagnetic force had a different strength, chemistry as we know it would be impossible. The precision is startling. In many cases, changing a constant by just a few percent would result in a universe radically different from ours, one where complexity couldn't arise. Some physicists have calculated that the allowed range for certain constants is extraordinarily narrow, like hitting a bullseye on a target the size of the observable universe. This fine-tuning has been used by some to argue for design, for a creator who deliberately chose these values. But the anthropic principle offers a different explanation, especially when combined with the mathematical universe hypothesis. If all possible mathematical structures exist, then all possible combinations of physical constants exist somewhere in the landscape. Most of these universes are barren, but somewhere in this vast space of possibilities, there are universes with constants that allow for stars, planets, chemistry, and life. We necessarily find ourselves in one of these rare, observer-compatible universes, not because they're special in any objective sense, but because we couldn't exist in the others. It's a selection effect. A fish might marvel at how perfectly suited its universe is for swimming, how water has exactly the right density and viscosity, how gravity is strong enough to hold water in oceans but weak enough to allow movement. But the fish exists precisely because it evolved in an environment with those properties. There's no mystery, no fine-tuning requiring explanation. The fish's existence selects for an aquatic universe from the fish's perspective. Similarly, we observe a universe with life-compatible constants because we're life. Universes without observers aren't observed. The appearance of fine-tuning is an artifact of observational selection bias. This explanation works only if there's a large ensemble of universes with varying properties. Without that ensemble, without multiple throws of the cosmic dice, the fine-tuning of our particular universe would remain mysterious. But if the mathematical universe hypothesis is correct, or if eternal inflation produces bubble universes with different constants, or if quantum branching creates multiple realities, then the anthropic explanation becomes viable. The anthropic principle doesn't tell us why any universes exist at all. It doesn't explain why mathematical structures have the property of existence, or why there's something rather than nothing. What it does is shift the question. Instead of asking why our universe has the specific properties it does, we can ask why observers like us exist to notice those properties. And the answer becomes, because in the vast space of possibilities, some universes support observers, and we're necessarily in one of those. Some physicists find this unsatisfying. It feels like giving up on finding a unique explanation for our universe's properties. It suggests we can never derive the fundamental constants from deeper principles, because they're essentially random, varying from universe to universe, with our values selected only by our existence. Others find it liberating. It removes the need for cosmic coincidences. It explains fine-tuning without invoking design. It fits naturally with theories like eternal inflation that already predict a multiverse. But both perspectives share a common limitation. They don't explain where the mathematical structures come from or why there's a landscape of possibilities in the first place. They describe how our universe might be one among many, but not why there are any at all. These theoretical frameworks offer different answers, but they share a common thread. They challenge our intuitive understanding of causation, time, and existence itself. We've traveled through several attempts to answer what came before the Big Bang. Eternal inflation suggests our universe is one bubble in an endlessly inflating expanse. Cyclic models propose that the Big Bang was merely one transition in an eternal sequence of expansions and contractions. Quantum cosmology hints that time itself might be emergent, making the question of before meaningless. Quantum fluctuations offer a mechanism by which universes can appear spontaneously from nothing, or at least from the quantum vacuum. And the mathematical universe hypothesis suggests that all logically consistent structures exist, with our universe being one among infinite mathematical possibilities. Each framework has its strengths. Each explains certain features of our cosmos. Each pushes against the boundaries of what we can know and test. But none of them provides a complete, definitive answer to the original question. Perhaps that's appropriate. Perhaps some questions live at the very edge of what's knowable. There's a fundamental limitation built into our inquiry. We observe the universe from inside it. We're made of the same matter, governed by the same laws we're trying to understand. We're trying to explain the context that makes our own existence possible, using minds shaped by evolution in this particular universe with these particular physical laws. It's a bit like a character in a novel trying to understand the author, or a program trying to comprehend the computer it runs on. We have access only to what's within our cosmic horizon, only to the physical laws that govern our region of space-time. Anything beyond that is, by definition, unobservable. This doesn't mean the question is meaningless. Science has repeatedly pushed past what seemed like fundamental limits. 1,000 years ago, no one could have imagined measuring the composition of distant stars. 200 years ago, the age of the Earth seemed unknowable. 50 years ago, detecting gravitational waves seemed nearly impossible. Each time, new technology and new theoretical insights opened doors that appeared permanently closed. The question of what came before the Big Bang might eventually yield to new physics, to a theory of quantum gravity that unifies our understanding of the very large and the very small. Such a theory might let us see past the Planck wall, might show us whether the singularity is real or an artifact of incomplete physics. Or it might reveal that the question itself is based on incorrect assumptions, that our intuitive concepts of causation and temporal sequence don't apply at the most fundamental level. Science is unusual among human endeavors in its comfort with uncertainty. A scientist can say, "We don't know," without embarrassment. Better yet, a scientist can say, "We don't know yet, but here's what we're doing to find out." The gaps in our knowledge aren't weaknesses to be hidden. They're opportunities for discovery, frontiers waiting to be explored. The theories we've discussed aren't failures because they don't provide final answers. They're remarkable achievements, extending human understanding into realms that seemed forever beyond reach. They show us possibilities we couldn't have imagined without the mathematical language to describe them. And they do something else, something equally important. They reveal that reality is stranger and more subtle than common sense suggests. Time might not be fundamental. Causation might be an emergent property. The universe might be one among many, or might exist within a timeless mathematical structure. These ideas challenge us to think in new ways, to question assumptions we didn't know we were making. There's also something profound about a universe that contains beings capable of asking about their own origin. You are made of atoms forged in stars, arranged by evolution into a configuration capable of pondering existence. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all were created in stellar furnaces billions of years ago. You are, quite literally, star stuff contemplating stars. That you can ask where the universe came from is itself remarkable. For 13.8 billion years, the universe evolved unconsciously. Matter clumped into galaxies. Stars formed and died. Planets coalesced. And on at least one planet, in at least one corner of the cosmos, matter became organized enough to look back at its own history and wonder. The question of what came before the Big Bang connects us to every human who has ever looked up at the night sky and felt that mixture of wonder and confusion. Ancient peoples created myths to explain creation. Philosophers debated whether the universe had a beginning or existed eternally. Now we have equations and observations, telescopes and particle accelerators, but the fundamental sense of mystery remains. Perhaps mystery is an essential feature of existence, not a temporary gap in knowledge that will eventually be filled. Perhaps there are questions that don't have answers in the way we typically think of answers. This doesn't make the questions less important or the inquiry less valuable. The pursuit itself expands our understanding and our sense of what's possible. Living with uncertainty requires a certain kind of courage. It means accepting that you might never know certain things, that reality might not conform to your intuitions or preferences. It means being comfortable with provisional knowledge, with probabilities rather than certainties. But there's beauty in this uncertainty too. It means reality is larger than our current understanding. It means there's always more to discover, always deeper questions to ask. The universe doesn't owe us explanations that satisfy our psychological needs for closure and comprehension. It simply is what it is, unfolding according to its own nature. As you lie here in this moment, in this particular arrangement of space and time, you're part of a cosmic story that extends backward through billions of years and forward into an uncertain future. Whether the Big Bang was an absolute beginning or a transition, whether it emerged from quantum fluctuations or was part of an eternal cycle, whether time itself is fundamental or emergent, you exist. You're here, conscious and aware, able to contemplate these questions. That might be the most profound answer of all. Not where everything came from, but the simple, undeniable fact that something exists rather than nothing, that the universe gave rise to beings capable of wondering about it, that you're part of an ongoing process of cosmic self-discovery. The question of what came before remains open. The mystery endures. And in that enduring mystery lies an invitation to remain curious, to keep looking up at the night sky with wonder, to accept that some of the deepest questions might never be fully answered, and to find meaning not in the answers we lack, but in our capacity to ask.